Okay, so let's get rolling. If you remember from last class, we created a new ability. Let's go into here, where when we run our game, we can, so let's see, right now I have a room to the north. I'm just gonna go north. So I have south or north. I have south or west, so let's go ahead and create a room to the east. So I'm gonna hit create. And it's going to want to know the room title. And frankly, I don't remember. So we got room 1, room 2, room 3. I think this will be room 5. So we'll call this guy room 5. What room are we currently in? We're in room 3 right now. So room 4 would be to our west. Room 5 would be our new one to our east. So we'll title it room 5. Its description will also be room 5. We have to give it a unique room ID, which right now we're having to remember that. That's why I just kind of went and did that mental math. Hopefully I got it right, that this is a unique room ID, R5. The idea here is that we would probably have like a hand-drawn map that we're trying to create in our game here. Press enter there. We're going to give it now the direction that this guy is going to lead to. So we'll say to the east. And then enter the direction leading back to this room. So we'll have it leading back to the west. All right, so now we have a new room to the east that we can take called room 5. And we can go back to the west. That takes us back to room 3. If we go to the west again, that should be our room 4 from last time. Yep. Okay, so now we've updated our map, but only in runtime, only with the thing currently running. If I quit the game right now and I don't change my code at all, so if I hit quit, it's just a quit command like this. I'll go ahead and copy this so I don't have to do it again, but we'll go ahead and run our program again, and I'll run up to the north again. And we see we still only have that exit to the west because all those changes we previously made, we only made during the running of our application. We didn't actually change our JSON file. So if I go ahead and quit the game, I go into map.json and I overwrite that file with my output from the previous thing and hit save. And then I run. Now I can go to north. And now notice I have a west and an east. So my new room is now there. So we have the ability to now build our rooms as we kind of go through. But we probably want to have some sort of ability to write that out to our map when we're ready to write. Now, last class, I think we looked at, was it under file test? Yeah, so we did the difference between writing and appending. We did this last time, right? Somebody give me a squeak or something.
Yeah.
Thank you. Okay, so the difference is if I open up a file for writing, it will always overwrite the file. Where if I open up a file for appending, it'll add to that file. Now, in this particular case, we do want to overwrite the file because our map.json thing here, this guy, he currently holds all the details of our entire map. So when we hit save in our game, we want to overwrite the entirety of this guy with our new map. Okay? Now, we already have the ability to output that map. We're doing it at the very end. We have a thing called map.toJSON. And that guy is getting us the JSON string representation of our map. So what we want to do here is when we go up to our map builder, let me just stretch this down a little bit. We want to build a command into our map that allows us to save it. So notice here that map builder, when we first create it, it brings in the file name. And he's opening that file, but he doesn't store that file name anywhere. We're going to need to use this file name later on for opening and writing that file. So what I'm going to do is I'm going to go ahead and remember that file name. So I'm going to say self.filename is equal to file name. So what this will do is I just added as a field to my map builder the file name that was passed in. That way I can use it inside of other functions inside of map builder later on. Okay, now right here where I'm opening the file, I can say self.filename, or I can just say file name, because variables resolve to their most local definition. So file name right here, its most local definition is right there. So he knows about that variable, but he also happens to know about self.filename because I said it right before this. So I can use either of those two right here. It doesn't matter which I use, but this line right here allows me to have access to that file name later on. Okay, so now what I'm going to do is I'm going to go ahead and build a save function for my map builder where I can tell an instance of a map builder to save itself, which will write it out to a disk. And we can decide if save is clear enough. Maybe we want to say write to disk. What this guy will do is it'll open self file name for writing. All right. Now remember, we don't want to forget to close that. And I believe it's s.close, or is it just close? s.close. So we'll go ahead and just create the sandwich at the end here. So we need to say s.close, because anything that we write to this file only happens in memory. The s.close is where it actually gets stored to the disk. All right, so we're going to open our file for writing. What are we going to write to it? We're going to say s write self.to JSON. And if you remember, we have a toJSON function here that is owned by this particular instance of our map builder. How does an instance refer to itself from within itself? By saying self. So this guy is saying call my toJSON function, which will give me a JSON string representation of myself. And that string is what I'm going to write to this file, and then I'm going to close that file. That's what write to disk will do. Okay, so we've added a new ability, a new method to our map builder that now knows how to overwrite the file he was built using with a new updated version of himself. So down here in our commands, we'll go ahead and add in a command here. The command is equal to save. We'll say the map dot write to disk. And then maybe we'll do a little print saying something like map saved, just to give us a little feedback that something did occur. Okay. So at this point, we now have a new command called save that I should be able to type. And when I type in save, we ask the map to write itself to disk. Writing itself to disk means that we will open the file name it was built using, whatever file name that was, because we can create multiple maps here. And then we can write to it the JSON version of the current state of our map. Any creates that we've done will be there. And then we can close it, and then that'll be permanent. So the next time we start our game, it'll read in from that now modified file. So we will see the updated version. So we'll go ahead and run this. We'll run to the north, and here's our southwest east rooms. So let's go ahead and create a room. And this room title will be room 6. Description will also be a very creative room 6. The room ID will be R6. The exit direction will be to the north. And the room leading back will be to the south. All right, so now we see that we have our new room to the north, and we can go ahead and test that, make sure it does what we want it to do. There it is. All right, so now if we're happy, we can go ahead and just type in save. And notice it says map saved here. All right, so I'm gonna go ahead and I'm gonna quit my game. I'm still dumping out the JSON version of this guy, but I'm not gonna copy it or anything. I'm just gonna go ahead and hit play again. And because we updated that actual file, we should now have that final exit to the north. So notice here we have our east and our west, as well as that new place to the north, because we did save our map. Okay, so imagine here that we have a pretty good way for us to build rooms and things like that. Okay, so questions about that. And we could certainly go on and give us the ability to destroy rooms or move rooms around or, things like that. So, I mean, hopefully we're seeing that the level of automation is kind of as much of as our imagination lets us go. We can kind of do whatever we want here. So what we're going to do now is we're going to switch gears a little bit. We're going to be talking about object inheritance. And if you remember way back when we created a room, we had something in here called list of inhabitants. Now, right now, our inhabitants are monsters and players, right? So we have a thing called a player, and players have a name, a hit points, and a current room. They can display themselves, they can deal damage, they can take damage. They can determine whether they're dead, and they can also have their current room set. Then we have a monster. A monster has a name and hit points. It has deal damage. It has take damage. It can return whether it's dead. So we see a whole lot of overlap between monsters and players. Okay, they're very similar to each other. In fact, a player knows about the current room that it's in, but realistically, if we think ahead a little bit, well, we ask the question, why does a player know about the current room it's in? Because players can move rooms, right? We just we can dash through our map here, go north, 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 whatever, and that is taking us out of a room and putting us into a new room, and then we become notified of our current room, which is the new room we're in. Well, right now our game has one monster in it, a rat. And we decided, you know what, that right now our rat only lives in a single room. He goes into the room that we put him in, and he doesn't travel to other rooms. One thing we want to look at here pretty soon is what if we want him to travel to other rooms? And we're going to look at that on Wednesday, doing something called multi-threading. But for right now, we want to come up with a better way of modeling players versus monsters. So what I'm going to do is I'm going to come back here, and we're going to say, for us right now, a player has a name, it has a number of hit points, and it has a current room. That's what a player is. Now I'm going to steal this, and if we just squint our eyes a little bit here, we're going to say a monster is the exact same thing. All we've added now is the current room, because if we decide that we want a monster to be able to change rooms, maybe he wanders around on his own randomly or something like that, where you're standing in a room and all of a sudden a rat walks in and starts attacking you or something like that. But in any case, maybe a monster also has a name, a hit points, and a current room. Now, we might say, well, what differentiates a player from a monster? Well, let's say that in your common video games, you get the ability to kind of build out your avatar and stuff like that. So we're just going to put something kind of a vanity thing in here. We're going to say a player also knows about hair color. All right, so that's what differentiates our players from our monsters. Is players have a hair color, where monsters they are what they are, for no good reason other than just forcing this example. All right, so we look at these two objects and we see that these guys have a lot in common with each other. All right, so what we can do, so if you look at our current code, we're actually writing the same code several times. We're writing it twice, once for player, once for monster, and there's tons and tons of duplicated code in there. We might say that one of the goals of object-oriented programming is to minimize the amount of duplicated code. We might even make a note and say, this is really a rule of all programming, which is why we have functions, right? When we have something that we might want to do multiple times throughout our program, we put it into a function so that whenever we need to call those 11 lines of code, we don't rewrite them. Instead, we just call the function. Okay, so this is really a rule of thumb for all programming, and object-oriented programming just takes it to the next level. It says, hey, if we're describing objects that are going to live inside of our program, and we have two objects that are extremely similar to each other, but they just differentiate themselves just a little bit, do we have a mechanism for representing that in object-oriented programming? And the answer is yes, we do. And it's something that we're already familiar with. We have something called inheritance. So just like in real life, we inherit some traits from our mother and some traits from our father, and that is who we are. So we get a little bit of both, and we're kind of a mixture of that. Well, the same thing is true here in our object-oriented programming. Now remember that programming languages attempt to solve problems in a similar way to how we already solve them in real life. All right, so again, always kind of remember that this tool, the programming language that we're using, it's trying to make our lives easy, okay? Because we already know how to solve problems in real life. And a lot of the problems we're trying to solve in code are, they're intimidating to us right now because we're not all that practiced with this tool. I kind of think about that in terms of like video games. So if you want to think about some of the challenges you go through with programming, like I consider myself a pretty good driver of a vehicle. So, I have a boat and I can back my boat around corners and up my driveway and zip it around the mailbox, and that's a pretty hard move to do. So, but now I go into a video game, it's like driving a car, where I'm not that familiar with the Xbox controller or something like that, and I'm terrible. I'm banging into things, I'm going into turns too quick, whatever it is. So even though I know how to drive, now that I'm having to solve that problem through the use of a different tool, I'm going to have to practice some to kind of get used to the buttons on the controller and the timing and things like that, because it's modeling, it's emulating that same maneuvers, but it's through a different mechanism. And that's why in real life problem solving is pretty easy for us, because we've been doing it for 20 years or 18 years for most of you, whatever it is, a long time, right? Where you've only been programming for like 14 weeks or something like that, a little bit different thing. So, once again, I want to reiterate this thing that you are supposed to suck at it right now. All right, so those of you that are still feeling overwhelmed and that you aren't good at this and, oh, I'll never catch on, you're right where you're supposed to be. It's supposed to feel difficult at this point. And eventually it'll become more and more fun as you feel like you can do more and more stuff without errors. All right, so stick with it and, you know, try to find as much joy in the process as you possibly can. But again, remember, you're not supposed to be great at it yet. If you feel like the stuff we're doing right now is easy, then you're ahead of the curve, and at some point it'll catch up to you and you'll start bumping into harder things. Okay. So the idea is, this idea of inheritance is something that's already common to us in real life. It's been something we learned when we were kids. All right, so now we have a tool inside of our programming languages, inside of object-oriented programming languages, that allow us to mimic this. All right, so let's introduce a couple of, so we have a tool that allows us to mimic this. And we do it when a class is initially created. All right, so what I'm going to do here is I'm going to create a little bit different model here for us for testing. That way I can give you the homework to do it for our bigger thing. So let's say that in real life, we have something called an automobile. Okay, so we have an automobile. Now, none of us actually own a generic automobile. We own a car or a motorcycle or a scooter, you know, a truck, you know, whatever we can. Let's just keep it car and motorcycle for right now. So in actuality, the automobiles that we have going around are cars and motorcycles. Okay, now what differentiates these guys from each other? Well, first of all, let's say, what do they have in common? Well, what they have in common is all automobiles have a number of wheels. All right, so they know how many, you know, a car has 4 wheels, let's say a motorcycle has 2 wheels, but they have some number of wheels. That's something that all automobiles have in common. They might also have a horsepower. All right, so how strong the engine is, something along those lines. And for any of you car people out there, we're pretty quickly going to be getting to the limit of my car knowledge. So if I say something stupid, just pretend like I'm dumbing down the example, but it ultimately comes down to I don't really know that much about cars. So I can handle number of wheels, and I know that typically more horsepower means the more you spend at the pump, but also the faster or more you can pull or whatever, depending on how the motor is tuned. So these are things, let's say, that are common among automobiles. Now, we could also maybe throw a third thing in here and say number of passengers. Number of passengers. Okay, so we'll say that all automobiles have a number of wheels, a horsepower, and a number of passengers associated with it. Now, how do cars and motorcycles differentiate themselves? And we might have to stretch this, you know, a little bit. So maybe we say that a car has a number of airbags. And maybe a car also has a number of seatbelts. I'm not sure if a motorcycle has seatbelts or airbags. I think in general the answer is no, but for this example, let's pretend like the answer is no. Does anybody happen to know? Do motorcycles have airbags and seatbelts? All right, so we're just going to assume I'm correct then. Or none of us know anything about motorcycles, one of the two. All right, so so now we want to think what differentiates a motorcycle from a car. You know, so now you know, we have to come up with something Maybe what are some things that a motorcycle might have that a car doesn't? Anybody have an idea? We need at least one thing that a motorcycle has that a car doesn't.
Saddlebags.
Okay, so that's like storage.
Yeah.
Saddlebags are storage compartments. All right, so number of saddlebags. Okay, so that's our storage compartment. So a car wouldn't have those, so we wouldn't keep track of the number of saddlebags. I'm guessing depending on the size of the bike, you might have a bag on one side or a bag on both sides or multiple bags on each side if the thing was bigger. And maybe even some motorcycles have kind of a trunky type thing, which we could just call another saddlebag. So they have some storage containers that do deviate based on the size of the motorcycle. We might say that's kind of like our trunk for our car, but let's just go with it for right now as being a difference. Okay, so in this model, let's say that this is good enough. We have a core class called automobile. We'll make that guy yellow. And then off of that, we have created two subclasses. A car is an automobile. A motorcycle is an automobile. So let's go ahead and let's create our class for an automobile here first. Let me go back here. And we'll just go into our file test. All right, so we're going to create a class called automobile. And we decided that an automobile would have a number of wheels, which is just going to be a number, an amount of horsepower, also a number, and a number of passengers, also a number. So it's going to keep track of 3 numbers. All right, so we're going to have our constructor. And this guy will take in a number of wheels, number of, what did I say, passengers? Number of passengers and horsepower. Number of passengers and horsepower. Okay, all automobiles will have those types of things. And we'll set self.number of wheels equal to number of wheels. Self.number of passengers equals number of passengers. And then self.horsepower is equal to horsepower. All right, so those are the 3 things we're going to take in for an automobile. All right, so we're going to leave it like that for now. We're not going to give any abilities to an automobile. Actually, let's give a display. Def display. Print. I am an automobile with so many wheels, so many passengers, and this much horsepower. So this will be self.number of wheels, self.number of passengers, and self.horsepower. Okay, so that will be my formatted string for outputting an automobile. That's what that little F beforehand is. It's a formatted string that lets me embed stuff in there instead of concatenating it together. So a nice little handy thing. All right, so now I can go ahead and I can test this. I can create a couple of automobiles, and we'll go ahead and do our main just to keep things consistent with what we've been doing. So we've been creating a function called main, and inside here, I'll create an A1 is equal to an automobile with 2 wheels. Let's call it 1 passenger. It'd be a smaller motorcycle. And I don't know, what's the horsepower on a motorcycle? Like 60 horsepower? Probably close. Small for a car. Let's just say that's it. And then we'll have an A2 is an automobile that has 4 wheels and can have 5 passengers and maybe has 150 horsepower. And then we have an A3, which is an automobile that maybe can hold 7 passengers. Oh, that's number of wheels. So 4 wheels, maybe 7 passengers, and has 300 horsepower. Something like that. You know, that would be like a big SUV or something. All right, but I've called them all generic automobiles. So now I should be able to say A1.display, A2.display, and A3.display. And when I run this, oh, I haven't actually called this. All right, so that's my main method. And then we do the little thing where we say if underscore underscore name underscore underscore is equal to underscore underscore main underscore underscore. If that's a true statement, then we'll call our main method. And now this guy runs. So that's that whole thing where all programs begin and end with main. And we prove it here with just asking a question inside the global environment in Python saying, if the name of the function that it's trying to call is underscore underscore main, I'll go ahead and pass it off to my local function that I named main. That allowed us to think about scopes and keeping these things separate, where anything I define here in main, A1, A2, A3, is not accessible anyplace else. All right, and we see that we get the output of 3 different display methods. I only wrote that method once. Here's my single display method, but I get 3 different outputs. Here's the first one with an automobile with 2 wheels, 1 passenger, 60 horsepower. Here's another one with 4 wheels, 5 passengers, 150 horsepower. And then here's another one with 4 wheels, 7 passengers, and 300 horsepower. All right. So what we want to do now is, rather than having to create automobiles like this, why don't we go ahead and make some classes that inherit from automobile? So since I've thrown an SUV thing in here, let's just update our picture here where we have a now an SUV that's kind of a bigger version of a car. Well, actually, we didn't even represent seatbelts yet, but that's okay. So maybe for an SUV, we also keep track of let's say maybe towing capacity, something like that. So an SUV is a car, which is an automobile. So we're going to go ahead and create this inheritance model. So we're going to create a car and a motorcycle, but they're going to be created in terms of something that we haven't actually seen before. When we create an automobile here, there's kind of a hidden thing called an object that shows up there. All right, this is the default object in Python. We don't have legal syntax for it here, but you know, this thing does exist. That there's this top level object that is the most generic object that can exist. We add it to our picture here. Just drop these down a little bit. We have something that lives above here called object. And let me try to make a guess at it one more time. Maybe it's lowercase o for object. Yeah, it looks like it might be right. Yep. All right, so an automobile is a generic object. So keeping the case sensitivity correct here, this is object. This is something that is built into Python, and this guy represents a generic object. And whatever that means, you know, that's the guy that creates the initial constructor, underscore, underscore, init, underscore, underscore. So he creates that basis for life in our object-oriented language. Okay, we don't have control over this guy. He's built into the language. He gives meaning to objects. All right. So when we create a class and we don't say anything special about it, it is assumed that this class inherits from a generic object. So an automobile is a generic object and then some. A car is an automobile and then some. An SUV is a car and then some. A motorcycle is an automobile and then some. Okay, so this is like an inheritance model that we can generate here. So given this optional format where I can say an automobile inherits from object, I don't have to say that, because if I don't put anything there, by default an automobile inherits from object. But now what I can do is I can go ahead and say I have a class called a car, and this guy comes from automobile. So he starts off as an automobile. Okay? And we've decided that automobiles they differentiate themselves because they have a number of airbags and a number of seat belts. So we'll have this guy take in a couple of parameters: number of airbags, number of seat belts. Now, reality is we could even say that we can extrapolate airbags and seat belts based on a particular car, but we'll pass this stuff in. Now, notice I didn't take in the number of wheels, because we can just say all cars have 4 wheels. We didn't take in a number of passengers because in our world we've decided that all cars can hold 5 passengers, let's just say. And we also decide that all cars are created equal and they all have 150 horsepower. All right, so now what we can do is we can build a car. Again, we've made this representation that a car is an automobile. So we're going to start off by building a car in terms of its parent. All right, we can do this 2 separate ways, but I'm actually going to do it in a way that is most consistent with how object-oriented languages work. So we have a keyword called super. Super is how an object refers to the instance of its parent from within itself. This is similar to the self keyword, which is how an object refers to an instance of itself from within itself. Okay, so self is how an object refers to itself from within itself. Super is how an object refers to its parent from within itself. Okay, because now this guy has a parent. Our other guy had a parent as well. If I was inside of automobile and I said super, I would be referring to the instance of object on which I was built. If I'm in car and I say super, now I'm referring to the instance of automobile on which I was built. If I'm inside of SUV and I say super, I'm referring to the instance of car on which I was built. Okay? So what we want to do here is, since a car is built in terms of an automobile and it shares all this stuff with automobiles, I want to go ahead and initially create my car in terms of an automobile. And we notice that automobiles have a constructor that takes in a number of wheels, a number of passengers, and a horsepower. So the first thing I'm going to do inside of my constructor for a car is I'm going to go ahead and refer to my parent, super. I'm going to call his constructor. And this guy takes in some parameters. So I'll go ahead and pass it 4 for the number of wheels, 5 for the number of passengers, and 150 for the horsepower. We're just going to say all cars share those things with each other. All right, so at that point in time, a car is a automobile, just the shorthand version of an automobile. So if I were to say A2 is equal to a car, and it's asking for a number of airbags. So let's say this particular car has 4 airbags and 5 seat belts. Let's just use that as an example. The number of seat belts should equal the number of passengers, but let's just say in our world, that's not necessarily the case. Certainly in the historic world, my dad tells me stories about drive-in movies where they had nights where it was, you know, a price per car or something like that, or maybe that's how it always worked, where they would pile as many people as they could into a car and get in for, you know, whatever the price was, and then everybody got to go to the movies for not that much money. And then they would sit on the grass or whatever, you know, watch it. But, you know, in any case, legally speaking, the number of passengers a car is rated for should equal the number of seatbelts inside the car by today's standards. Okay, so right now A2 is actually a car. Now, I'm going to go ahead and run this, and notice that here is my A2 calling his display method. Now, did I write a display method inside of car? I did not. But because he inherited from automobile, he became everything that an automobile started off as, including he got automobile's display method. All right, so a car is being built in terms of an automobile, but now I said I actually want to differentiate cars just a little bit from automobiles. So I'm going to add a little bit more. So I'm going to say a car also keeps track of a number of airbags. And he also keeps track of a number of seatbelts. Okay, so now I'm remembering 2 additional pieces of information that our parent did not know about. So I asked my parent to go ahead and build me the core portion of myself in terms of my number of wheels, number of passengers, and horsepower. And then I'll think about my specialness here with these other 2 things. Okay. And then what I'll go ahead and do is I'll go ahead and I'm going to override the display method. And for right now, I'll just print out woot in here. All right, so for car, I already was passing in number of airbags and number of seat belts. I'm still not using those. I am remembering them, but I'm not using them anywhere. But now notice that my output for car calls woot. Because just like variables resolve to their most local definition, when a function is called, it resolves to its most local definition. And for a car, in this case, A2 is a car, his most local definition of display was actually created inside of himself. Instead of us looking in here for a display, not finding it, and bouncing up to our parent, looking for it there. All right, so now we get a more local version of display. But what if I want to do both? What if I want to display my automobileness, but then I want to display a little bit extra? What I can do is I can say, super, call your display method, then I'll put a little pizzazz on the end. So notice now that a car has 2 lines. It has the output from his parent's display method, and then he goes ahead and puts a little extra in there. Okay, and we could do that in either order. So if I want to say woot first, or I am a car, and then call my parent's display method. There's my I am a car. And then here's the output of his parent's display method. Now, realistically, maybe we want to do something like show our parents display method because we are an automobile, but then we want to go ahead and print some additional stuff like our number of airbags. So like I also have self.number of airbags, and self.number of seatbelts. Okay, so now when I print out the car, here's my car stuff. It shows me my automobileness, but then also adds in that it also knows about airbags and seatbelts for this car. And notice I was able to build a car with less pieces of information. Similarly, I can create a class called an SUV, or sub. Well, almost lunchtime, I guess. And this guy is actually a car. So his constructor is not going to take in, let's see, what I have SUVs doing. They had a towing capacity. All right, so this guy took in a towing capacity. That's all an SUV needed to be created. And he's going to have a, we're going to go ahead and call his parents constructor, which is car. So the parent constructor takes in a number of airbags and a number of seatbelts. So for an SUV being a little bit bigger, let's say his number of airbags is, I don't know, 7, and number of seatbelts is, I don't know, 9. Let's say we have some extra seatbelts in there for some crazy reason. All right, so that's how we build a car. And then we'll say that we also have a towing capacity of towing capacity. And then we can have a display method that calls our parents display method, which then calls his parents display method, which then displays information about his carness. And then I can also say print I have a towing capacity of self.towing capacity. So now I can say A3 is an SUV with, let's call it 5,000 pound towing capacity. And when I run this, notice I have, he's an automobile, he also has some airbags, he also has a towing capacity. All right, so here's an example of the inheritance model where we have a top level object that automobile inherits from by default. A car is an automobile and then some, and an SUV is a car and then some. All right, so I'll put that up as your starting point, but then for your homework, update our game to have a top level class called inhabitant that holds all of the commonalities of players and monsters, as well as, well, let's see, then create classes for player and monster that inherit from inhabitant and then differentiate themselves in some way for right now. eventually we will have our monsters kind of moving around independently. That's what they'll be differentiated as, whereas a player is moved based on human beings controlling them. All right, so I'll put up this current code from today that shows you the inheritance example. All right, and then your homework is to update our game to have a top level class inhabitant that is kind of like our automobile class here. And then two additional classes, player and monster, which become automobiles. All right, questions, comments, concerns, bribes?
I have a question.
Sure.
So if you don't have like set numbers in the init files for things, would you have to pass like an SUV, like number of wheels, number of passengers, horsepower, number of airbags, number of seat belts?
Yeah, if you wanted to hold all those pieces of information, yes.
Okay. Okay.
But in this world, we're saying that all cars are this. So we can hard code those. That means that the person creating a car needs to pass in less information.
Okay.
All right, anything else? All right, I will see everybody on Wednesday. Today is Monday, right? I got that right?
Yes.
Thank you.